Welcome back. We are all set to start the new module on nuclear medicine, right? So as per our flow of contents, right, we will start nuclear medicine with first talking about the physics part of it, a quick overview, and then physics, and then the different uh, submodalities. The nuclear medicine is one big branch. Within that, what are the different techniques that are used to acquire, right? So different images that you can get. So we will go in that order. So what we will do first is start with overview and then physics, spend some time on planar scintigraphy. It's like and then on your T's, very similar to the template that we followed, right? X-ray imaging, so physics we covered, then projection radiography. After projection radiography, we started to talk about the tomography part of it, right? So similar order we will cover here, and then conclude with image quality considerations for PET and PET. Okay, so let's get ourselves introduced to nucleide imaging, right? In fact, we introduced this in some sense during our introduction. So it's going to be a quick overview of what it is. So what is nuclear medicine? I mean, nuclear medicine might seem like it's medical subspecialty, right? That's how it is used, nuclear medicine. We are engineers, so why is it nuclear medicine? I mean, traditionally that's how it has been housed. But our interest, we want to look at it from a nucleide, also known as nucleide imaging. So what is nucleide imaging? The name is very suggestive, right? Imaging of the nucleus. So what we did so far, we will again review that, but we were talking about in X-ray in the earlier modules about X-ray. We were more interested about the electrons, right? Now we should be more interested in the nuclear aspect of it, right, of the atom. So quickly, this is the logic. So you here what is happening is, we actually send some radio tracers, radioactivity, all these terms we will kind of describe in this module to begin with. But essentially you are sending some radioactivity into the body in the form of radio tracers. After that, what happens is, you give it some time, it will distribute itself, right? So you introduce radioactivity into the body, that substance will distribute because you put it in the blood, it will go through wherever the blood is taking it and get used, right, or get accumulated or go to location where it is used, right? So, and then because this is radioactive tracer, it is going to give out radioactivity, or it is going to give out gamma energy. So it is going to give out gamma energy. So when we detect this gamma energy, our interest here is not in the energy per se. Our interest is, after you detect the gamma, where is it coming from, right? That is our interest. So you give some time, right, for uptake, metabolism to happen. After that, you detect the regional variation of this activity, right? And the idea is, the presence of absence of any activity can be tracked by the variation in the uptake, right? So detect regional variations of radioactivity as an indication of presence or of absence of a physiological function. So the key message here is, even before we said X-ray, X-ray came out on the other side and we detected, and we said, oh, depending on the attenuation, we could tell what is that, depending on the number of photons that are received, right? On the detector, we used to tell what is the attenuation along the path. So it was a distribution of mu in X-ray energy. Here, on the other hand, we are not really interested in the attenuation of the or what is the mu or anything. Here, the activity is coming. Our objective is to say where that activity came from, because that activity is indicative of some action. So this is functional imaging. This is the key. So this is very important, functional imaging. So whatever we did in X-ray, it was through transmission. You sent through, got the energy on the X-ray energy on the other side, whereas here, as you can see in this diagram here, the source is sent into the body, right? Source is sent into the body. Your objective is to detect where the source is. So based on the detection, you have to locate where the source is. So it's slightly different way of looking at things, but it gives very powerful look. For example, so you have some instrumentation which we will cover, and then you transform this to an image. Notice here, right, there is a region that is high activity. Say for if you have a tumor, right, cancerous tumor, you know cancers tend to grow aggressively, so they are metabolically more active. So when you send a radioactive tracer, it will go accumulate more, right, in the region where there is more metabolic activity. So the radioactivity will come from more from this location, because the radio tracer that you sent is supposed to go there. Okay, so you engineer it so that it goes to that location. Okay, good. So we'll go into all these terms that I said, right? Radioactivity, tracer, giving out energy, gamma rays, detector, all this we will cover. Okay, but this is the rough idea that we want to know. So once this gamma rays come, we can either use gamma camera or a detector array. So how we did for chest X projection radiography, right? We got a X-ray imaging, we got an image, or in CT, X-ray CT, we detected it and then did a reconstruction. So we'll do similar things here. In one we call as scintigraphy, the other is your PET or SPECT, depending on what you are reconstructing. Okay, so so much for the introduction of what we are. It's a big picture overview of what we are going to cover. So just to relate it to what we have covered so far, or what you know from X-ray CT, right? Where are the difference? So in projection radiography, right, what we covered projection radiography and tomography. So that was a through transmission image, that is the key. Okay, and most of the time what the images that we showed, right, it was structural imaging or measuring the anatomical structure. Okay, whereas in nuclear medicine, as we just saw, this is about detecting the gamma rays, but this is from inside, emitting from the source inside the body. So this is a emission imaging. Okay, it's not through transmission, this is emission. So you send the radioactive tracer into the body, and it starts to emit gamma rays. So you are essentially catching the emissions. So it is called as, where is the emission coming from? How much of emission is coming from where? That is what you are capturing. So it is your emission imaging. Again, like we talked about, it's a functional. So you are not really talking about anatomical contrast here. You are not actually trying to measure the tumor dimension, right? You are trying to capture, or you are trying to see the tumor based on the activity that is happening. So you are not going to measure the tumor size based on this image. For that we can use CT. We are going to capture the activity of the tumor, that you can use PET. How metabolically active is the tumor, that you can catch from PET. Okay, so it is actually, so there are several other applications, brain perfusion, myocardial perfusion. This is another important. So whole body. In one of the introduction slides we showed PET, you can use it for whole body, right? So you can actually detect where all the activity is, it will light up in the body. So it's a very good modality to capture or see the metastasis, meaning a primary tumor is there and it goes, branches out, tumors come in different locations. So you can do a whole body PET scan, you might find out possible locations where that cancer is active. Okay, so by itself it's a functional image, anatomy is not the main interest. So usually what happens, so this is example of a PET images and the color scheme that it's usually plotted. So you can notice that of course bladder will show up, anything that you take it's going to come to the bladder, right? So you can always catch up in the bladder. but the key difference here is this is the corresponding attenuation image or from your CT. Notice you see so much details here which is actually not present here. So typically you also call what we call as a PET CT, right. So they fuse these two images, it's a multimodal imaging, here it's dual mode, PET and CT scanner. So PET CT scanner essentially tries to register the PET on top of a CT so that you get both structural image and functional aspect of it. So this is very powerful. Clearly you can appreciate this image gives you lot more information than either of the two images in isolation. Okay. So it has a very powerful, very clinically significant applications. And so what we will try to do now is step in and understand what is the physics. That the first part that we said, right, here we understood attenuation, that forms the basis for the image, the pixel. If you see, right, where does it come from, what is the meaning of the pixel, what are the units of the pixel, all that we covered, right. Hopefully you are able to appreciate that. So we will try to now do the same thing. When you see a red color or a yellow color or bright yellow, what does it mean, what are the units of that, how did we get it, what all does it capture, how all it got, how can I increase it, decrease it, right, what plays a role in that. So all these aspects both from physics, fundamental physics, and then the instrumentation and imaging and image quality we will cover for, of course this is PET, we will cover for nuclear medicine. This is only one of the more, one of the techniques in nuclear medicine. Okay. Fine. So what we will do now is get to the same slide that we started with, right, with the atomic structure. What you notice is this is the same slide. What we were focusing on in the previous module with X-ray, we talked about only the electrons and how the energy, X-ray energy interacts with these electrons. But now the focus is going to shift to the center. Okay. So we are going to now talk about the nucleus part. What is there? Oh, you have protons and neutrons. You have protons and neutrons. So now we need to address the similar question. Okay, we also talked about stable nuclides, right. Of course, we will pay now attention to this approximately equal to, that is one take home message you will get across. But there is a relationship between neutrons and protons for the nuclei to be stable. Okay. So if under certain conditions you can have unstable nuclides. So if a nuclide is unstable, that atom is called as radionuclides, radioactive atoms. Okay. So what is the big deal about this? Oh, the big deal is something is stable. We talked about this also for the whole of electrons interactions, right. If something is unstable, the nature has it that it will come back to stability by sending out the excess energy, right. This is the big picture philosophy, right. You have to give out the energy to come back to ground state, which is usually the more stable state. So likely to undergo radioactive decay, right. So the radioactive element, radioactive atom sends out the extra energy, comes back to ground state. Okay. So we will see what kind of atoms, of course we talked about unstable nuclides give rise to radioactive atoms. So we will see the conditions under which this happens, or some of the radioactive atoms and elements and how it can be engineered, we will look at it. So before we jump in, there are several different terminologies, small variations in the number game, right. So what is an isotope? You have the same mass number, you have the same atomic number but different mass number. So here for example, right, you have carbon 12 or carbon 11. Carbon is the same element, so chemically identical. Okay. So these are called isotopes. But you could also have what is called as isobars. Oh, it's here is the thing, right. So, atoms with the same mass number but different atomic number, right. So, if it is a different atomic number, we also have, we said this, right, redundant information. So, now boron, carbon, we also named it. So, carbon, boron, these are different elements, but they have same mass number. So, these are called isobars. There are a few more isos that we will cover. Okay. So, isotones. So, we were even talking about mass number, sorry, electrons and protons, right. Electrons, protons, or your nucleus, right. But in the nucleus we start to have protons and neutrons. Isotones, what happens? Oh, isotones have same number of neutrons but have different A, right, mass number. So, within the neutrons, right, within the nucleus you have neutrons and protons. Here is a case where isotones, atoms with the same number of neutrons, but it has a different mass number. Isomers, oh, this is another interesting aspect. Isomers, it has same everything, same Z and A, but it is at a different energy level. Okay. So, these are, these are interesting because these are sometimes used in the process that we are going to look at, right. So, sometimes these come out because of the decay process. Okay. So, there are several isos that you should be very familiar. It is slightly confusing, but then when you look at the context and see how it is exploited, I think it will become, you should be able to get over that confusion. Okay. Okay, so much for the different types. So, now what we need to talk about is, okay, we have radioactivity. So, you have unstable nuclides, it has to shed energy to become stable. So, this process, right, you have some radioactivity. So, we need to define why is this is happening, or where all this energy, right, the excess energy to shed, where is it coming from, right. We talked about similar thing, binding energy, when we talked about in electrons, right, electron binding energy. Now, our interest is in the nucleus. So, we need to talk about two concepts, one is mass defect, the next is its equivalent, binding energy of the constituents of the nucleus. So, what is mass, the mass of an atom, right? Oh, we know mass of all these, right? Have you heard of atomic mass unit, right? You would have heard about that, right? So, it is 1/12 of the carbon 12, right? That is what we use as a units for talking about the mass. But it turns out that, oh, you have a mass, but then I have the constituents, right, which are electrons, protons and neutrons. Each of these particles have a mass. So, what happens if I sum the masses of the constituents of the atoms, right? Atom consists of these components, right, these constituent elements, particles. So, if I add them, that should be the mass of the atom, but that is not the case. The sum of the masses of the constituents is actually greater than the atom's actual mass. Okay. So, it turns out, let us take the example, right. So, this difference is called as the mass defect. So, there is a difference between the sum of mass of the constituent particles and the actual mass of the atom. These two are different, and this is called as the mass defect. So, let us take, I mean, because carbon 12. So, 1/12 of carbon mass is your atomic mass unit, right. But actual, right, that is your atom's actual mass. But what is the mass if you calculate based on the constituents? So, you have 6 mass of protons plus 6 mass of electrons plus 6 mass of neutrons. If you add that, you are actually getting 12.098934 AMUs. Oh, this is clearly different from 12 AMU, right. So, there is a fraction, there is a small difference. This is called as your mass defect. So, what does this indicate? Where does this extra mass, right, Actual mass is only 12, but when you add all this, it comes to this much. And we are talking about this excess mass, and we loosely said there has to be something to do with the energy states. So how do we connect the mass and energy? Oh, we know that, right? E is equal to mc square. So we can connect mass and energy using the equation, famous equation E equal to mc square. Therefore, this mass defect, right, this mass, extra mass, accounts for missing energy, which is called as the binding energy. So when it is binding, right, it has shed this extra energy. You can look at it that way, right? So when it is intact, right, together, that's how we talked about even electrons. When the electron was part of the atom, it was at low energy, correct? You had to supply energy to bring free the electron. So when it came back in, it shed the excess energy. Similar concept, right? So here there is a mass defect. This mass defect has a equivalent energy. That is the one that is binding the constituent particles, right? So binding energy. So the relationship between mass and binding energy is from your E is equal to mc square. So if you take one unit, right, we have always talked about energy in terms of electron volt. That is how we have been defining in this imaging system physics, right. So when we do that, one units has about 931 million electron volt. So that means your mass defect is going to correspond to, so your 0.09893 whatever, that is a small mass defect, right. That mass defect is going to correspond to 92.1 million. What is this? Oh, that excess energy, that is your binding energy, okay, that is your binding energy. Of course, instead of talking about binding energy, clearly the heavier the atom, right, more number of constituent particles, probably the defect is also going to be little more, and therefore your energy could be more. So instead of reporting just that, in normalize binding energy per nucleon, okay, per nucleon. So what is the nucleon here? Oh, you have 12, 6 protons and 6 neutrons. Put together you have 12 particles in the nucleus. So you have your 92.1 is the energy, that is a defect, whatever, mass defect, right, from the mass defect. That energy is your binding energy per nucleon, per 12 constituent neutrons plus protons is about 7.67. So essentially you will notice that if, right, you will kind of notice a behavior like this with, say, this is your number of nucleons, and this is your binding energy per nucleon, right. So you will have several elements. So this is a behavior that this depicts, okay. So it does not really increase or anything, it has an increase and then it kind of plateaus. So you have a list, in fact there is a table, you can find this plot with exactly which element is lying where, okay. But the idea here is nuclear binding energy required to separate P and N, the constituents of your nucleus. So the radioactivity, right, the radioactive decay can be thought of the process in which you have the unstable, right. So it has to rearrange itself so that it comes to ground state, inherent lower ground state, okay. So there is this rearrangement in the nucleus so that you get to a lower energy state. So if it is unstable, it will become stable by shedding out the excess energy. How does it come down? It rearranges the constituents. So this nuclear binding energy, so very equivalent to, I mean analogous, I should say, analogous to the concept of electron binding energy that we saw, right. So, and then it had to rearrange, in the process it gave out the excess. Similar thing happens here, but this is now happening in the nucleus. Okay. So, we can actually look at now, make this, remember I told about this number of protons is approximately number of neutrons, and I said we will look at that relationship between neutrons and protons, right. So, we have two types of nucleides, two groups of nucleides. One is stable, the other is unstable. So, the stable is fine, these are considered non-radioactive. We are more interested in the case which is radioactive, or rather these are unstable atoms. Okay. So, now the question is what kind of atoms? So, when we talk about unstable atoms which are radioactive, can we talk about their stability? We just talked about their binding energy and number of nucleons, right, binding energy per nucleon. Is there any clue on what could be unstable, right? So, that is where this concept of line of stability comes in. Line of stability comes into picture. So, here, so before you jump, this line which seems, this is not the line of stability. Line of stability is actually this curve that you see. So, what is this? This is a plot between number of protons and number of neutrons, the two constituents of your nucleus. So, now you notice when it is a smaller atom, probably this is along the line, but as the size increases, right, as the number of protons increases for the atom, right, it becomes a heavier element, your actually number of neutrons should be slightly more than your number of protons, so as to be stable. So, these are stable nucleides. So, it is not, even though it is called as line of stability is not a line, right. Line of stability is basically telling if how much more neutrons should I have for a given proton, so that this nucleide is stable. So, in some sense this is the line Z equal to N. Here you are talking about stable means it is actually having more neutrons than protons as you increase the mass number. Okay. So, this is a very important concept, because as you will see, the whole idea about, you can now start to think about radioactivity as nothing but, right, the stability or instability, that you can start to think about in terms of the atom wanting to rearrange the neutron to proton. So, if I am here, for example, right, I am unstable, I may want to have, right, protons. So, I may want to convert some proton, some way rearrange, so that I want to get to this line to become stable, right. So, I have to increase the neutron, decrease the proton, right, to reach this line. So, how this rearrangement takes place, we will talk about that, but the idea is this line of stability is important, because that tells you when an atom is. So, you can think about radioactivity as the process by which the atom tries to abide by this line of stability. It rearranges so that it forms on this line. So, that is your line of stability. Now, we need to talk more about, we talked about radioactivity, decay, it is trying to rearrange itself, very loose terms. So, we will now use the next few minutes to organize our thoughts into terminologies that will be consistently used. So, radioactive decay. What is the radioactive decay? It is the rearrangement of the nuclei to low energy state. So, we will have what is called as a parent atom. Parent atom is a radioactive unstable atom. What will happen? It will shed the energy and give out daughter atom, right. The daughter atom is supposed to be more stable, or in other words, you can also view it as daughter atom has higher energy, higher binding energy per nucleon, higher binding energy per nucleon. Remember the other concept, binding energy per nucleon we talked about, right. So, that again you can also view it like that. So, if you have more binding energy per nucleon, then it tends to be at a less energy state, right. So, you can also view it in terms of binding energy per nucleon. So, daughter atom has higher binding energy per nucleon, and therefore, it is more stable. Okay. So, becomes more stable. So, so when the parent atom decays, you get daughter atom, and the daughter atom is more stable. So, meaning you can think about it as having higher binding energy per nucleon. Okay. So, this rearrangement takes place. So, naturally that means in this rearrangement energy is released, right. So, when we talk about this radioactive decay, we talk about some disintegration takes place, right. So, you have this atom parent atom becoming daughter atom, that means this atom is disintegrated to while it is giving that energy out during the radioactive decay. Okay. So, we can think about it in terms of or radioactivity in terms of number of disintegrations per second. Okay. So, radioactivity, when you say it happens, what is happening? Oh, this parent atom is giving daughter atom, so it is disintegrating. How many disintegrations per second happens? That talks about your radioactivity, how active, right, number of disintegrations per second. So, radioactivity, number of disintegrations per second, is there any units? The SI unit is 1 becquerel or equal to 1 disintegrations per second, or more commonly what is used is Curie, right. So, naturally these two are related, right. 1 Curie is 3.7 into 10 power 10 becquerel. What is this Curie and becquerel? Oh, these are all named after doyens, right, people who actually did contribute to these concepts. So, becquerel and Curie are in honor of, right, people who contributed. Naturally occurring radioisotope was discovered by becquerel. Artificial radioisotope was produced by Curie. So, the units of this disintegration, right, SI unit is honored with becquerel, but more commonly the dosage that we are using, right, we tend to use millicurie, Curie, millicurie, especially in bioimaging we are talking, most commonly in terms of Curie. Both are heavy hitters who contributed to this. Okay. So, that is your radioactivity. Okay, fine. So, now we slowly are getting into the nitty gritty. So, we got the radioactivity, we know this energy shedding. So, we have some names, right, we have some units. So, what do we need to, before we jump in completely, what is the idea here? So, you give some radioactivity, right, we talked about giving a unstable. So, now so you are going to give some radioactive tracer into the body and the radioactivity is happening. That means disintegrations per second is happening. That means while it is disintegrating, it is giving excess energy out. So, what is the intensity? So, this energy comes out and you want to detect it. So, what is the intensity of radiation incident on the detector? So, let us say if the detector is kept at some r distance from your radioactive source. Same concept we use, right. You have a source, you have a detector, how much will be right, what will happen? Is there any law that comes into your mind? Exposure, right? When we talked about, what did we say? Oh, stay away, every distance you have safety of 1 by d square, inverse square law. So here also the same thing holds good, but what is your intensity? Oh, intensity has to do with number. In our previous X-ray when we covered, what did we say? Oh, number of photons into number of energy per photon. Here activity gives rise, right? So number of activity times energy per activity. So number radioactivity, right? Number of disintegrations. So each disintegration it is giving some h mu out. That is your energy. So this is your inverse square law, 4 pi r square. Remember, so this is the intensity that will fall on the detector when you have r distance due to radioactivity. Okay. Of course, A is your radioactivity of the material. So now you see the problem. The problem is I can give, okay, I have some radiochemist background, I am putting some radioactivity. You saw all the laws, how to make it radioactive, how to make it unstable so that it becomes, it will give radioactivity. So you are a radiochemist, you know how to work with it, you engineer a compound, engineer an atom, you give it, then it gives out energy. So now the task is, how do I detect this and say where it came from? Okay, these are the important aspects. So you know how to measure radioactivity, that is the goal, right? So I know the intensity. So if I know my intensity, if I know my distance, if I know my energy, if I know, I mean, what you see, this is very important. What is it that we need to know from here? What is the known, what is the unknown? So this you are going to measure radioactivity and energy per. So we need to still go into details to see how, what decay happens, what is the energy that is coming out, this we need to understand. Of course, this R comes into business when we do the geometry, right? Where do we place the detector, instrumentation, and then perhaps from there we can talk about where the source is located. Okay, so we will get to that. Clear? So we need to measure this radioactivity. So let us talk about when you measure radioactivity, right? When we did this for X-rays, what did we do? We sent an X-ray, we detected the X-ray. What happened to the X-ray? Oh, it got attenuated along the material, and so we used, that is our information, how much of attenuation happened through the material, or the material property was characterized in terms of its ability to attenuate the X-ray energy. So the mu was the material property that we were going after. Here what is the problem? I am not actually going after the material property of the tissue. All I am interested is, I have engineered this radioactive material, I have put it in. I want to know, when you put it into the body, where is this radioactivity coming from? So when I put it into the body, it will go through the body, it will distribute itself, and it will perhaps go to locations where it is going to be involved and the radioactivity is going to come from there. So my objective here is to detect the radioactivity is coming from where, how much of radioactivity is coming from which location. That is my, I am not really interested in the attenuation property of my tissue. Clear? So here what you want, so there why I said that is, you had your mu, your attenuation, we came up with a fundamental attenuation law which was exploited. Now here attenuation is not the big deal. Here there is a fundamental, what is that we are interested? We are interested in the radioactive decay, that is what we are interested. So there is a fundamental radioactive decay law that we need to put here, so that can be exploited for imaging. So what does that state? That says, okay, you have, you start with, says the n number of radioactive atoms at any given time, right? What is radioactivity? Disintegrations per time. So it's your A of t is your radioactivity, is proportional to number of radioactive atoms. that are there at that time. Okay. So you can write A, your radioactivity, I mean just pretend that n is continuous. Okay. So you have rate of change. So your radioactivity is number of disintegrations, right. So in time how much number of atoms change. So A is equal to minus dn by dt, right, is equal to your lambda n. So lambda is your decay constant. Okay. So if this is the case, then we can quickly look at it and rewrite, right. What do we want? We want what are we looking at? Oh, we are looking at when we did the X-rays, right, X-ray energy. We were looking at how much we sent, how much came out after it crossed the material. Here we have a radioactivity and we have some time. So after some time, how much of radioactivity is left, is happening. Okay. So because you send the radioactivity in, you give it some time, it goes redistributes itself. After that, radioactive decay is happening and you are detecting it. So you are interested in the decay, how the decay rate, how do you capture it over time. Okay. So from here we can talk about n of t is n naught. So this is from your boundary condition, whatever at t equal to 0 when you started, whatever was there, right. Number of activity is e power minus. So here also you talk about say exponential decay, that is what is happening. So the radioactivity is happening so that you have a exponential decay model. So your A of t is activity you start with at t equal to 0, right, and then it decays with a constant lambda, and therefore you can have A of t equal to whatever you start lambda n naught e power minus lambda t. Clear. So this means you start with some activity, it starts to decay, this is exponential, so it is never going to go to 0. There is some radioactivity that is going to be always there, right, it is never going to go to 0, but it will become insignificant after some time, right, and that depends on your lambda. What is that time depends on your lambda, that is the inherent property of that atom. Okay. So the number of photons generated during this time, what is the number of photons that are generated? Oh, it is decaying and it is sending out, right. So number of photons generated is going to be number of disintegrations that has happened, right. So how much is it going to be? Observe some time, radioactivity is number of disintegrations per second. So I want to see number of disintegrations over t, just integrate the activity over time, right. So you integrate the activity over the given time, which you call as the number of photons that are generated. Clear. So you have some photons n0 at t equal to 0 radioactivity, this is radioactive atoms, 1 minus e power minus lambda t. So n naught minus n naught e power minus lambda t is your leftover. So the number of photons that are generated, which is equal to your number of disintegrations. Clear. So fine. So this is actually a good place to just quickly think about one concept. So when you talk about starting point and right after some time this much radioactivity has happened. When we talked about the analogous concept, when we did X-ray imaging, when we talked about number of photons that go in, fundamental attenuation law e power minus mu delta x, and what comes out. We talked about an important metric as okay, how much is the material, how much the material. So we talked about mu as a material property. Here we are talking about radioactivity as the property, and we have this fundamental law. So natural quantity of interest is Oh, when is it 50%? There we talked about half value layer thickness when the attenuation was 50%. Here likewise you start with some N naught, some radioactivity. When does it become half, right? That is a quantity of interest. So half-life is the time it takes for the radioactivity to decrease by half. Okay. So same concept, how do you do? Oh, we start with the previous equation, right? We need T half. T half is nothing but you start with some A0, when does it become half? A T half. So ratio is equal to 1 by 2 e power minus lambda T half. So essentially it depends on the material property, right? There we talked about half value layer thickness. When we talked about inherent material property was the mu. Here radioactivity. Okay. So this again has similar workings, right? So you have a half, you have a E. So we could do this ln and we can get the value. So T half is 0.693 by lambda. As a formulation, this looks exactly same, I should say similar, just because here instead of lambda we had mu, okay, instead of lambda we had a mu, whereas here it is lambda. Otherwise the quantity of interest is half life, there it was half value layer. So this half value, both are exponential models. Okay. So what does this signify? So this signifies, again, this lambda is the constant, radioactive decay constant of that material, radioactive atom. So the atoms change their radioactive decay, some can decay very fast, some can decay slow. So now you see the issue. So you can send some material which is radioactive. That material, what is that material property of interest to us? Is the, depending on its decay rate, right? It is going to give so many, it is going to decay at certain rate, which is going to give you number of photons that are coming out at that rate at certain energy, and you have to capture that and say, so you cannot want the, so we will talk about the importance of this parameter, right, when we get slightly ahead. So the ideal characteristics, or what do you want of this parameter? See, the idea is mu we couldn't really change much because it was inherent distribution. Of course, there also we did change. We sent a contrast agent that was finely tuned. Here you are actually engineering it and sending it, so you have little more leverage. Okay. So as long as we understand what this is, we can also discuss about the desirable properties of a atom, say what should be a good value for lambda, and that maybe we can send it. Okay. So we will stop right here. What we will do next is, we will understand, we said decay, but we didn't really go into the details. How is it, what are the modes of decay? What are the different types of decay that are possible? What are the energy levels that are coming? Right, these are, we just said decay, energy level comes out, but we need to be little more specific on that. So we need to talk about modes of decay, what are the energy that comes out, and then similar to previous X-ray photons, right, you have to talk about energies that are coming out, energy packets that are coming out. So when this decay happens, what energy comes out? Is there any probability, randomness in that? Okay. And after that you really think about the photon energy, the interaction with the body is not much. We have already covered that when we talked about X-ray photon. It's just that it's going to be of higher energy, as you will see. So that will be for the physics. So we'll continue on the modes of decay right after this. Thank you.